Thank you again. My talk today will be about superconducting nanowires, specifically about their properties in the so-called insulating state. My talk is based on a work which was done in collaboration with Andrei Semyonov and Andrei Zaykin from the theoretical side, and with the experimental group of Konstantin Arutyunov from the other side. The outline of my presentation is the following. First, I'll provide you with some background into the theory of fluctuations in superconducting nanowires, which was already at least in part covered by Andrei Semyonov. And then I'll move to the probably more interesting part about the experiment of Konstantin Arutyunov group and discuss interesting things which we observed there. As you know, there are two distinct types of fluctuations in superconducting nanowires. The first one is smooth fluctuations of the order parameter, and the second one is phase slips. I'll just briefly cover that. Smooth fluctuations of order parameter can be further separated into fluctuations of the absolute value of order parameter and phase fluctuations. Modulus fluctuations and the associated Higgs mode is massive, so they are usually disregarded in calculations because they cannot be excited at low temperatures. And furthermore, they are controlled by a dimensionless parameter, which we call Higgs, which is usually large in experiments. On the other hand, fluctuations of phase are usually relevant, as in one dimension they are massless and they got sound like spectrum. And the corresponding mode, which is called the Moishan mode, is a sound-like mode which propagates with constant velocity. It also should be said that Moishan mode fluctuation magnitude is controlled by another dimensionless parameter, which we call G, and it's equal to the ratio between the quantum resistance unit, the normal quantum resistance unit, and the wave impedance of the wire. And it scales as the square root of the cross-section area of the wire. And usually in experiments, it is so that the G psi is quite large, but G is smaller, and the fluctuations of phase are much more relevant. Okay, and Andrei Semyonov told us much about phase slips some time ago. So I'll just briefly remind you that at low temperatures, phase slips can be excited by quantum fluctuations, and their amplitude is exponentially small and is given by this gamma QPS. What's also important that QPS processes are vortices in space-time. And if you calculate the action between two phase slip processes, it depends logarithmically on the distance between them, which leads us to the following physics. So here is the action of the sine-Gordon type, which describes phase slips. Okay, as we know, if we've got a two-dimensional electron gas with a logarithmic interaction, then we've got a BKT, Berezinski-Kosterlitz-Taulis phase transition, which is related to vortex binding and unbinding. It also can be seen from the exact solution of sine-Gordon model or from renormalization group studies. Well, anyway, in our system, a quantum phase transition occurs, which is driven by the parameter G. And there are two phases. If the nanowire is sufficiently thick, so that G is larger than 16, we are in the superconducting phase. In this phase, quantum phase slips are bound in tight pairs of opposite charges. So a phase slip which changes phase by plus 2 pi is followed by a phase slip which changes phase by minus 2 pi. And they do not change the properties of the ground state of the wire significantly. and may be treated perturbatively. So we can at least calculate something in this regime. The most important effect of QPS, quantum phase slips, is that in this regime, the wire acquires resistance, which depends on temperature. So here you can see that this resistance is quite small, it's proportional to gamma QPS square, and also it depends on temperature as a power law at low temperatures. And it also tends to zero as the temperature goes down to zero. So that's why this phase is called superconducting, at least because at temperature close to zero, the wire doesn't have a resistance. And if the wire is sufficiently thin so that G is less than 16, we arrive to a different picture. First of all, well, either from renormalization group studies or from the exact solution, we get that the excitations in the system are no longer massless, no longer soft. They acquire mass because the most basic excitations in these systems are now solitons and their bound states. And this mass is shown here. You can see it's also quite small, and it turns to zero at the transition point. Also, a new length scale appears associated with this transition, which we call LC, and it's a critical length. And it is exponentially large and actually diverges near the transition point. The meaning of this coherence length is that the phase coherence decays exponentially at long distances, and one may say that phase coherence is localized on length LC, or Q pairs are localized on this length LC. What I should also say about this state, that since we now have got mass in the excitation spectrum, we expect that the resistance of the nanowires at low temperatures now doesn't go to zero, but it oppositely goes to infinity. So this state is truly insulating even at low temperatures. So it seems that the superconductivity in the insulating phase is completely lost. Well, it turns out that it's not that simple. About 8 years ago, there was an article by Andrei Semenov and Andrei Zaikin where they considered a QPS ring, just a closed ring with quantum phase slips pierced by a magnetic flux. And they found that it can still carry supercurrent at zero temperature. What's interesting that this ring can carry supercurrent not only in the superconducting state, where actually quantum phase slips do not almost affect this current. It's interesting that there is dissipationless current also in the insulating state. However, if we take the circumference of the ring large, then this supercurrent decays with the length exponentially as exponent of minus L over LC. So we see that superconductivity somehow survives in this phase if we consider a specific kind of experiment, a flux-biased experiment, and if we consider that the sample has a finite length. So this leads us to the conclusion that locally superconductivity may survive even in this phase at zero temperature. Okay. So we see that quantum phase slips affect physics of superconductors globally at large scales. And at small scales or locally, physics is already affected by the Moishan mode. In 2017, we published an article where we explored the effect of smooth phase fluctuations on local properties of the wire, specifically on the density of states. And I just briefly show you the results, what should be expected. So as you see, Moe-Shon modes in superconducting nanowires form an intrinsic dissipative environment. So they produce some phase decoherence, and it leads to a broadening of the density of states. The result of the calculation is the following. As you can see, at any finite temperature, the singular coherence peak and density of state gets smeared, and we get an exponentially decaying sub-gap tail in states. So we expect to observe it in experiment, and I will indeed show that it is so. Furthermore, even at zero temperature, the effect persists, and it is so that states are driven from the peak region to higher energies. It's not seen here, but they just move to higher energies. And this behavior is governed by parameter g, and at certain value of g, the singularity gets completely destroyed. However, superconducting gap remains well defined at zero temperature. Okay, now let us move to the experimental part of my talk. Here on the left side, you can see pictures of the experimental setup. So the upper panel is the scheme. As you can see, there is a large aluminum superconducting electrode, which is connected by tunnel junctions to several long and uniform superconducting titanium nanowires. And it's possible to perform two types of measurements on these nanowires. First, longitudinal resistance of these nanowires was measured as a function of temperature. And secondly, tunnel current voltage characteristic of the contact between titanium and aluminum was also examined. And below you can see just the image of the structure. The parameters of the wires are the following. They are 20 micrometers long. Well, probably the most important is that they've got quite similar width, which range from 30 roughly to 65 nanometers. And that this width of titanium nanowires is much smaller than the superconducting coherence length, which is estimated to be 150 nanometers. So from the point of view of the order parameter, these nanowires are one-dimensional. However, the electron mean free path is around 5 nanometers here. So it is much smaller than the transverse size of the sample. So the sample is, all the samples are three-dimensional from the point of view of electrons, and we can use usual formulas. Well, and it's not really seen here in the image, but you can see that the aluminum wire is much wider. And it also has larger TC and larger gap. So if you calculate the magnitude of fluctuation effects there, you can come to the conclusion that they are much weaker in aluminum, and we can completely disregard them. So, so we study fluctuations only in titanium. Also, an important fact is that the dimensionless conductance G for all the titanium samples lies in range from 1 to 3, which is much less than 16. So all these samples should be deeply within the installation state. Okay, let us now turn to the measurements. First, we will consider the dependence of resistance on temperature. And here are 5 different wires presented in this graph. So you can see, you can clearly see that these wires fall into 2 categories. There are 2 samples which exhibit a sharp resistance drop below the critical temperature, which is about 400 millikelvin for titanium. But there are also 3 wires which almost do not exhibit any kind of drop and remain resistive down to lowest temperatures. And you can also see that the difference between their widths is not as large. So what happens here? So we try to perform some fitting of these samples and found out that these 2 more superconducting samples are well described by the thermally activated phase slips theory. So this resistance drop below TC is described by this kind of formula, from which we are able to extract the parameter G psi of the wire. If we could measure resistance down to lower temperatures or down to smaller wires, we should see the transition to the QPS regime, so the curve should become less steep. However, we do not really see it here because we reach the experimental zero faster. However, we can just see that the red curve just slightly diverges from the TAPS prediction. Well, and I also should say that it's impossible to fit these 3 insulating, well, less superconducting samples with this formula, because it's a quasi-classical formula and it relies on the fact that the exponent is large, and for these samples this exponent is not large. So we cannot really fit them in any way. This fit allows us to estimate, well, although we do not see quantum phase slips directly here, these measurements anyway allow us to estimate some parameter of QPS. And in this case, we were able to extract the lower bound of the critical length for the sample T2, which is the red line here. So if we assume that the transition occurs just at the level of experimental zero, we get that the critical length is around 12 micrometers. And if we do not make such an assumption, it's just the lower bound. And if you remember, the length of the sample is 20 micrometers. So for the sample T2, this critical length is roughly of the size of the sample itself. So if we take into account that these samples vary in width, we get that the violet sample T1 is much shorter than its respective coherence length, and other 3 samples are, on the contrary, longer than their coherence length. And in our opinion, this explains this drastic difference between these resistance curves. So the BKT quantum phase transition is essentially an interaction effect, which appears only on large scales. It again can be shown either from remuneration group studies or other methods. So if the sample is much larger than this critical length, we indeed get the picture of the quantum phase transition where samples turn insulating. However, if the sample is shorter than this coherence length, then the interaction between quantum phase slips does not develop, and they can still be treated perturbatively. So for samples shorter than the coherence length, we anyway get the perturbative result and arrive to the conclusion that their resistance is exponentially small and proportional to gamma QPS squared. And on the other hand, longer wires, or wires where critical length is small, are resistive down to lowest temperatures. Perhaps I should add that we do not see the resistance upturn at low temperatures, probably because well, the experimental part of us couldn't reach low enough temperatures. because the emergent gap associated with solitones is very small, and it's indeed too difficult to reach such temperatures. However, as far as I remember, the resistance upturn was observed in at least one of the experiments, so probably the insulating picture holds, but it requires smaller temperatures and really long samples. Now, I am going to show you the measurements of tunnel contact, so the tunnel current voltage characteristics. In the left panel, you can see the IV curves for all these samples which were present in the previous slide at the lowest temperature, which is said to be around 21 millikelvin. So it's possible to notice that if we sort these samples from the thickest to the thinnest, then the peak broadens. If the sample becomes thinner, the peak broadens. And we can also see this decaying tail of states on the right, which shows us that the states leak under the gap. So I probably should remind you that this is the superconductor to superconductor tunnel junction. And if we take two BCS superconductors, then even at finite temperatures, you should have a discontinuous jump at voltages which are sum of gaps of the two superconductors. However, if this result is smeared by fluctuations, we get a broadened peak, and that is exactly what we observe here. In the inset of the left figure, you can see the IV curve for a single sample, for the one of the resistive samples, in a logarithmic scale. And you can see that the dependence is exponential. These dots lie almost on a single line, and if you consider its slope, it corresponds perfectly to the theory I outlined above. Okay. And we also tried to fit one of those, well, several of those curves by our theory, and got a qualitative correspondence. So on the right panel, you see the fit. And in the inset, you can see the reconstructed density of states. And you can see that there is a well-defined gap. Even though fluctuations are large and the coherence peaks are completely smeared, the temperature is low and the gap persists down to the lowest temperature. So perhaps it should also be noted that these fits yield the value of G, which is very close to the theoretical estimate. So we believe that it's a signature that we are right. And also we should know that there is no qualitative difference between samples which are longer than LC and shorter than LC. As you can see, these curves are similar, they just become a bit wider. And the last thing I want to show you that there are also samples which support Josephson current. Unfortunately, it wasn't observed in all the samples, but there are several samples which show this peak in current voltage characteristic at 0 voltage. And on the right, you've got it magnified. So the Josephson current in such structures is very small, and here it's around 5 picoampere, which is roughly 2 or 3 orders of magnitude lower than it should be by Ambikar-Baratov formula. But again, it's expected because there are large fluctuations and they suppress Josephson current. And here you can see the resistance curve of this sample, and you can indeed verify that it's not really superconducting. So below the resistance, so the resistance doesn't drop to 0 fast. It's like more into the insulating regime. Okay, and this leads us to the conclusions. So at G equal to 16, an infinitely long, even uniform wire undergoes a BKT phase transition. And below this phase transition, a critical length appears, which can be seen in resistance measurements. On the other hand, local properties of the wire, such as density of states, do not change qualitatively with this transition. At least it seems so. The samples do not really feel this critical length. Also, the wire retains the ability to conduct dissipationless current along a finite segment, although its value is significantly diminished by fluctuations. So the samples in this regime demonstrate a puzzling mix of long-range phase suppression and short-range superconductivity. And if you wish to see more details, then you should look up this our recent paper. Okay, thank you very much for your attention. I will be ready to answer all your questions.